September 8, 1945. The outskirts of Nagasaki, Japan. The wind carried ash through the valley, fine and gray like powdered bone. Professor Nishina Yoshio stepped from the military truck onto ground that still radiated heat through the soles of his boots 3 weeks after the detonation. Around him stretched a landscape that his physicist's mind struggled to reconcile with known reality. Buildings had not merely collapsed, they had been erased, their molecular structures disrupted at such fundamental levels that stone had liquefied and steel had vaporized. Trees stood as charcoal silhouettes, their shadows permanently burned into pavement that had bubbled like tar. Nishina had spent the war years leading Japan's own atomic research program, the NIGO project, racing against rumors that the Americans were pursuing the same terrible physics. He had worked with limited resources, minimal uranium, and the constant awareness that Japan's industrial capacity could never match the theoretical requirements for a functional weapon. His team had concluded it would take a decade, perhaps longer, to build a single atomic bomb. Now he stood in the ruins of Nagasaki, where everything he had calculated, everything he had believed possible, had been rendered obsolete by a weapon that had obliterated 24 square miles in a microsecond. The silence was total. No birds, no insects, just the whisper of radioactive dust settling over a dead city. Nishina knelt and ran his gloved hand through the ash, and in that gesture of a scientist confronting the unknowable, he understood that Japan had not lost a war. It had lost an entire epoch. For 3 years, Japanese scientists had worked in the basement of the Institute of Physical and Chemical Research in Tokyo, theorizing about atomic fission while American counterparts mobilized the largest scientific and industrial project in human history. The contrast was not merely one of scale, but of philosophy. Japan's atomic research was theoretical, academic, conducted by brilliant minds working with slide rules and chalkboards, but almost no practical resources. The NIGO project had access to less than 20 grams of uranium oxide. Cyclotrons for isotope separation were primitive, prone to failure, and operated intermittently due to power shortages. When General Tojo's office inquired about the feasibility of an atomic weapon in 1943, Nishina had delivered a sobering assessment. Possible in theory, impossible in practice, given Japan's industrial limitations and the scarcity of materials. The Americans, Nishina knew from pre-war academic exchanges, had the industrial capacity and the uranium reserves. But even he had underestimated what American abundance could accomplish when directed toward a singular purpose. The Manhattan Project had not been a research program. It had been an industrial mobilization that treated atomic physics like an assembly line problem, throwing $2 billion and 130,000 workers at challenges that Japanese scientists had deemed insurmountable. Nishina's investigation team moved through Nagasaki with Geiger counters clicking their staccato warning, measuring radiation levels that confirmed what the destruction already announced. This had been an atomic explosion, a sustained nuclear chain reaction that released energy equivalent to 21,000 tons of TNT in a fraction of a second. The bomb they called Fat Man had detonated 1,650 feet above the Urakami Valley, and the physics were unmistakable. The characteristic heat flash that had ignited fires 4 kilometers from ground zero. The pressure wave that had propagated outward at supersonic speeds, creating overpressures sufficient to collapse reinforced concrete. The ionizing radiation that had killed thousands who survived the initial blast, their cells destroyed by gamma rays and neutrons. Every measurement, every data point, every sample of irradiated soil told the same story. The Americans had successfully weaponized atomic fission, and they had done it not once, but twice, 3 days apart. The implication was staggering. If, America could produce 2 atomic bombs within 72 hours. How many more waited in reserve? Dr. Arakatsu Bunsaku, another member of the scientific delegation, stood before the ruins of the Mitsubishi Steel and Arms Works, where factory buildings had been flattened into geometric patterns radiating from the hypocenter. Arakatsu had led the Rewritten, rival FGO atomic research project for the Imperial Japanese Navy, working independently from Nishina's Army-sponsored program. The two teams had competed for resources, rarely shared findings, hampered by the same institutional fragmentation that had plagued Japan's entire war effort. Now, standing in the atomic wasteland, such rivalries seemed obscene. Arakatsu removed his protective mask and breathed the contaminated air, a gesture of defeat. He had believed, as they all had, that atomic weapons were a theoretical possibility requiring resources beyond any nation's capacity to mobilize during wartime. The ruins before him proved otherwise. America had not merely built an atomic bomb. It had industrialized the process, created an entire infrastructure for producing fissile material, and deployed the weapons with the casual efficiency of a nation that possessed more where these came from. The symbol that haunted every Japanese scientist in Nagasaki was not the bomb itself, but the plutonium that had fueled it. Fat Man had been a plutonium implosion device, far more sophisticated than the uranium gun-type bomb dropped on Hiroshima. The Americans had not only enriched uranium to weapons-grade purity, a process Japanese scientists knew required massive centrifuge arrays. They had also constructed nuclear reactors to breed plutonium, extracted it through chemical separation, and machined it into a sphere surrounded by explosive lenses that compressed it to critical mass. The technical challenges were exponential. The industrial requirements were astronomical, and the Americans had overcome all of it while simultaneously fighting a two-front war across 2 oceans. The plutonium sphere at the heart of Fat Man represented a level of industrial and scientific integration that Japan could not have achieved if given a century of peace. Nishina's team collected samples from the hypocenter, where shadows of vaporized humans were imprinted on stone steps, negative images preserved by the thermal pulse. These were not casualties of war in any traditional sense. They were physics, experiments, human bodies subjected to temperatures and radiation doses that transformed them into data points. The measurements would later reveal that Fat Man had been even more efficient than Little Boy, converting a higher percentage of its plutonium core into explosive yield. The Americans had not merely succeeded in building atomic weapons. They were iterating, improving, treating nuclear physics like automotive engineering. Japan's scientists had been playing chess while America played industrial assembly line. The emotional transformation was not immediate, but cumulative. Nishina returned to Tokyo and briefed what remained of the military leadership, presenting data that left no room for interpretation. The atomic bombs were real, reproducible, and represented a weapon against which there was no defense. Japan's vaunted spirit, its willingness to sacrifice millions in homeland defense, its bamboo spears and suicide tactics, all had been rendered irrelevant by physics. You could not outspirit thermodynamics. You could not banzai charge gamma radiation. The atomic bomb had severed the connection between courage and military effectiveness, revealing that modern warfare had become a contest of industrial and scientific capacity in which Japan was not merely losing, but playing a fundamentally different game. Army officers who had argued for continuing resistance, who had dismissed Hiroshima as perhaps a unique weapon, fell silent when confronted with Nagasaki's data. 2 bombs, 3 days apart. And the Americans had threatened more, promising a reign of atomic destruction until Japan surrendered unconditionally. But it was not just the weapons themselves that shattered Japanese scientific confidence. It was the system that had produced them. Nishina had visited American laboratories before the war, had corresponded with Oppenheimer and Fermi, had witnessed the open exchange of ideas that characterized Western scientific culture. The Manhattan Project had succeeded not despite American democracy, but because of it. The project had mobilized universities, private industries, and government laboratories in a coordinated effort impossible under Japan's rigid military hierarchy and institutional tribalism. Scientists had been empowered to make decisions. Resources had been allocated based on need rather than bureaucratic politics. Problems had been solved through collaboration rather than competition. The atomic bomb was not merely a weapon. It was the physical manifestation of a social system that could channel individual genius into collective achievement, that could turn theoretical physics into industrial output, that could make the impossible routine through abundance of resources and flexibility of organization. Dr. Sagane Ryokichi, who had studied at Berkeley under Ernest Lawrence before the war, wrote in his journal after visiting Nagasaki, "We were not defeated by American bombs. We were defeated by American universities, American factories, American openness of thought. We hoarded our small knowledge in isolated programs. They shared everything and built an atomic city in the desert. We calculated that enriching uranium was impossible without consuming our entire electrical grid. They built new electrical grids just for the enrichment plants. This is not a difference of dedication or intelligence. This is a difference of systems, of ideology made manifest in steel and uranium and plutonium. The plutonium became the recurring symbol in Japanese scientific discourse after the war, representing not just a fissile material, but a philosophy of abundance. Plutonium did not exist in nature. It had to be created in nuclear reactors, bred from uranium through neutron bombardment, extracted through complex chemical processes, and refined to incredible purity. The Americans had built reactors at Hanford, Washington, specifically for plutonium production, vast concrete structures cooled by the Columbia River, operating around the clock to transmute elements. They had constructed an entirely new industrial infrastructure to manufacture a material that had never existed on Earth until human ingenuity forced it into being. And they had done this as a secondary track, a backup plan in case uranium enrichment proved insufficient. Japan's scientists had not even attempted plutonium production. They lacked the reactors, the chemical expertise, the engineering capacity. The plutonium core of Fat Man weighed 14 pounds and represented a level of industrial sophistication that summarized everything about the gulf between American and Japanese capabilities. In the months after surrender, as American occupation forces arrived and Japanese scientists were interrogated about their own atomic research, the full scope of the disparity became clear. The Manhattan Project had operated 3 major sites: Oak Ridge for uranium enrichment, Hanford for plutonium production, and Los Alamos for bomb design. Oak Ridge alone employed 75,000 workers and consumed more electricity than most nations generated. The K-25 gaseous diffusion plant covered 44 acres under one roof and processed uranium through thousands of stages of isotope separation. Japan's entire atomic program had consisted of 2 small teams, perhaps 50 scientists total, working in university basements with equipment that would have been considered obsolete by American standards. The comparison was not even humiliating, it was absurd, like comparing a bicycle to a locomotive and wondering why one moved faster. Nishina Yoshio died in 1951, his health ruined by radiation exposure from the investigation of Nagasaki and years of working with primitive cyclotrons without adequate shielding. Before his death, he established himself as an advocate for peaceful nuclear research, arguing that Japan's future lay not in military ambition, but in scientific cooperation with the West. He had seen firsthand what happened when scientific and industrial might were mobilized for destruction. He had measured the temperatures, calculated the radiation doses, walked through cities transformed into open-air laboratories for the study of atomic effects on human tissue. And he had understood, with the clarity that only direct observation can provide, that the atomic bomb was not an aberration, but a preview. America had not strained itself to build these weapons. It had allocated a fraction of its wartime budget and succeeded in revolutionizing warfare. What else might such a system accomplish? What other impossibilities might American abundance and democratic organization overcome? The ruins of Nagasaki were eventually rebuilt, though the hypocenter remained preserved as a memorial, a park where the atomic bomb had detonated. Markers showed the radius of destruction, the concentric circles of devastation spreading outward like ripples in water. But for Japanese scientists who visited in later years, the memorial represented something beyond the obvious horror of atomic warfare. It represented a fundamental truth about industrial modernity, that theoretical knowledge meant nothing without the capacity to implement it, that brilliance without resources was merely an academic exercise, that in the contest between systems, the one that could mobilize, coordinate, and produce at scale would always triumph over the one that could merely imagine. The plutonium sphere at the heart of Fat Man had been 8 inches in diameter. That small mass of artificially created element had released energy equivalent to the entire conventional bombing campaign against a medium-sized city. And somewhere in America, production lines were making more plutonium, more bombs, expanding the arsenal with the methodical efficiency of a nation that treated atomic weapons as it treated automobiles. ATC manufacturing problem solved. Through application of resources and systematic organization, Professor Yukawa Hideki, who would become Japan's first Nobel laureate in physics in 1949, wrote in the 1950s about the lesson of the atomic bombs. We believed that spirit could overcome material disadvantage, he reflected. The atomic bomb taught us that in modern warfare, material is spirit. The nation with deeper resources, more flexible thinking, and better coordination between science and industry does not merely have an advantage, it inhabits a different universe of possibility. Japan entered the 20th century believing it could adopt Western technology while maintaining Eastern philosophy. Nagasaki proved that technology and philosophy are inseparable, that the weapons a nation builds reflect the society that builds them. America did not win because Americans were smarter or braver. America won because American society was structured to mobilize knowledge into power, abundance into weapons, democracy into coordination. The atomic bomb was not a secret stolen or a trick performed. It was the inevitable output of a system that we had fundamentally misunderstood. On that September day in 1945, as Nishina Yoshio knelt in the radioactive ash of Nagasaki, measuring radiation with instruments that clicked their warning of invisible death, he was not merely documenting a destroyed city. He was witnessing the end of one era and the beginning of another. The era when courage and determination could compensate for industrial weakness had ended at 11:02 a.m. on August 9th, when a plutonium sphere compressed to critical mass had released the binding energy of atomic nuclei. The new era belonged to those who could harness the fundamental forces of nature, who could build cities in deserts dedicated solely to producing materials that did not exist in nature, who could coordinate thousands of scientists and engineers toward objectives that seemed impossible until they were accomplished. The plutonium sphere, that 8-inch ball of transuranic metal created in reactors, cooled by American rivers, and refined in American laboratories, was the perfect symbol of what Nishina and his colleagues had failed to understand about their enemy. America's power was not brute force. It was systematic, scientific, abundant, and above all, it was organized. The atomic bomb did not merely explode. It announced. It declared that the nation which built it possessed resources beyond calculation, coordination beyond comparison, and a willingness to transform the theoretical into the operational that no amount of spiritual dedication could match. In the ruins of Nagasaki, Japanese science confronted American industry and learned that in modern warfare, The laboratory and the factory were not separate domains but integrated systems, and the nation that integrated them most effectively would write the rules for the world that followed. The mushroom cloud that rose above the Urakami Valley was not just destruction. It was demonstration, and every Japanese scientist who measured its aftermath understood, with the clarity that data provides, that they had been playing in a different league, operating under different assumptions, and the game had been over before they realized it had begun.